Thank you all very much. Thank you for coming. This is my first department colloquium, so it's exciting, and it's really an honor to be doing it for a department of the caliber of A&M. So thank you all very much for your time. Hopefully, I'll make it interesting. Um, so I'm going to talk today about trying, what I would call is like a broad early like career goal for me of trying to fix what I think is a problem in like the process that we typically employ when we work with modeling spatial data or data that's irregularly sampled or whatever, right? Which is that I think, oftentimes we write the model before we have a good exploratory tool to decide what feels like an appropriate parametric family to use or something like that. And so in particular, I'm going to be thinking about Gaussian processes today. And so I'm sure many of you are familiar with this already, but just a quick definition, a Gaussian process is some process whose finite dimensional marginals are multivariate normal that satisfy some kind of consistency requirements. Certainly, one easy way to satisfy those requirements is to adopt a parametric function that defines these pairwise covariances so that I kind of automatically satisfy the Kolmogorov conditions and whatever. I'm going to call that covariance function K, and I'm also going to assume for this entire talk, for some reasons that will become clear, that this function K is shift invariant in the sense that I can write it in this single argument form that takes like a lag instead of two locations. And so, I mean, for this entire talk, I'm going to assume I'm stationary and also that I mean zero. I'll talk about some extensions and complaints one might have about that setting later, but for now, that's how I'll develop some theory. And so the typical GP workflow, right? And again, I'm sure many of you are very familiar with this already, right? Someone hands you some data that's observed at some collection of locations, right? Sea surface temperature, ocean drifter, whatever, right? Like you get some things, you don't get to decide where the measurements are made very, very often. And they say, okay, I want to know something about the process. I want to make some predictions somewhere. I want a confidence interval for these predictions, or I want conditional simulations or whatever. And so ultimately, you need to somehow specify a joint law between data you have and data that you wish you had, in some abstract sense, at least. And so the pipeline that someone typically does, for spatial data at least, is they first pick a valid parametric family of covariance models. And I'll give you some examples of that later. And then and I know this is a strong Bayesian department, so I really should have said one option would be you compute the MLE. I am not a literate Bayesian myself, so I hope you'll all forgive me for assuming that everyone's just going to compute an MLE. But you select the best member of your parametric family based on some criterion, we'll just say, right? And then you pretend like that covariance function with those parameters is the truth, and you do whatever your downstream tasks are. I'm going to address bullet point 1. I'm sure everyone has looked at bullet point 3 and thought at some point someone should do something about the kind of like plugin error that is also being incurred that we're just completely ignoring. And I also think that would be nice, but I have no idea how to address it effectively. So I'm not going to say anything about that. But if anyone does have an idea, I'd be very curious to hear about it. So I mentioned this valid parametric family of covariance functions, right? And so the rub here in defining a covariance function is that it needs to be something that yields a positive definite matrix for any collection of locations, and that is a very abstract property for a function to have, right? It's not pointwise in a sense that you can check easily. It's not something that can be validated very easily. I mean, it's easy to write something that looks like it should be a valid covariance function and is for small matrices, but then eventually it isn't, or something like that, right? Like in a time series class, maybe someone gives you the AR1 with a parameter that's the correlation that's too big, too close to 1, and then you make the matrix big enough, or something like that, and you just start to squeak out some negative eigenvalues. Like it's a challenging task. And so what do? We just pull something off the shelf. We pull some standard thing off the shelf, right? And so the typical options. Anyway, the typical options that you'd see 99% of the time are the ones that I'm showing you here. And I think secretly the behavior of all of these 4 models is effectively contained in the behavior of this just the Matern model, right? You only get a few dials to turn. You have some kind of correlation length scale. You have some kind of marginal variance, and if you're lucky, you get something to play with the mean square differentiability of your process, which is important. But that's not hugely expressive, right? And so many times, what people elect to do is instead work with the Fourier transform of a covariance function, which under some reasonably mild conditions, you can represent in this very nice way with a function called a spectral density. And what's nice is that for a covariance function, its Fourier transform is characterized in terms of nice pointwise properties, right? Non-negative. If k is real, then S should be symmetric naturally, right? But things that are easy to check and easy to then, like you could kind of look at that and you can write a parametric family that is symmetric about the origin and non-negative without a ton of pain, right? And so it's hard to do, but in the time domain, but injecting useful degrees of freedom into a model is very easy to do in the spectral domain. So for example, this is from a paper that I'm not going to talk about today about kind of rapidly computing many Fourier transforms. But I think this is just like a fun example for why one might want to go spectral. I think something that many people frequently say is, I'd love to write a covariance function that can take meaningful negative values, right? And why shouldn't we? And if you go back to that list I showed you of covariance functions that are kind of the stock off-the-shelf ones, none of them take negative values. Certainly you can multiply any of those by like a pure oscillatory term, and by the Schur product theorem kind of conclude that you've made something that's a covariance function and has oscillatory, but that's not a very useful form of being oscillatory, I think, or at least it's very restrictive. But in the spectral domain, you can get weird. And so in this example I show you here, I can make that dip pretty near the origin that goes well below 0. I can make it very large, and I can not introduce like an oscillatory tail, and you can do all sorts of kind of nice things. And so happy to chat offline about the Psycho project for evaluating these Fourier integrals for slowly decaying and singular functions at millions of locations rapidly. But just to say, like, what I'd like to set up is, and maybe I should just keep going. I'm jealous of what the time series people can do regularly, right? And to me, the thing that I like so much about time series analysis is that spectral density estimation in a non-parametric way works so well, is so well studied, and is so easy to use and employ to create a pipeline that I think scientifically makes sense. So if you're a time series person and someone hands you data, or at least, I mean, okay, what would the first thing I would do be? I would look at a non-parametric spectral density estimator, right? So in this example, I've got some data here, and I would compute this thing that makes no parametric assumptions, right? It costs 1 FFT and a little bit of other work, and I'd instantly look and I would say, okay, I've got that sharp peak in the spectrum at this frequency where just looking at the data, I think you could entirely miss that, or at least I would, right? So if you fit some kind of just generic Matern model or whatever, you'd miss this incredibly strong feature in the data. But looking at this non-parametric estimator, you could then look and say, okay, now I'm going to build a functional form for my model, right? And I think I just like that this workflow where the exploratory stage then informs the model building stage, and then you fit your model and you do some downstream tasks or whatever, right? Like that's what I want to do with spatial data. I don't want to pick the one covariance function that I happen to know how to use, and then kind of like force that square peg into a round hole no matter what the data looks like, right? And so in this talk, I'm going to talk to you really about, I'm going to focus on this first step here of bringing this exploratory analysis of potentially irregularly sampled data in time or space-time or whatever, kind of up to parity with what lattice data applications can do, right? I want to take something that looks like an FFT, and then I want to look at that estimator and say, here are features that I think my model should have, And so let's dive in. So these spectral density estimators, in the case of time series data, we have something on a lattice, and we'll say we have no gaps for convenience, right? They effectively look like weighted DFTs of your data, right? And so what one typically, like when you introduce this in a class or whatever, or like in Brockwell, people typically pick a window function G, and then they pick weights that are just G on this equispace lattice on the unit interval or something like that. And the relevant thing to think about here is this thing called the spectral window, which I think some people write the squared modulus of what I'm calling H alpha. I think they maybe call that the spectral window. Hopefully, this notation, I'm going to be consistent about saying H alpha is not the squared modulus of that thing. But what's relevant here is that the expectation of your estimator is the convolution of the squared modulus of your spectral window with the true spectral density, right? And so that is a very elegant and pleasant result. And as you might expect, then, if I want a good sharp estimator for my spectral density, then I want to choose G so that the corresponding H alpha is as close to a delta mass at the origin as possible, right? And so for regrettable, Heisenberg uncertainty reasons, this is not possible to do exactly. But you can also imagine that there are better and worse functions that you might choose to try and get close to that, making that delta mass, right? And so I'm showing you a few kind of classic examples here. So, if you use flat weights where that's just 1 over root n or whatever, that would be your periodogram. I'm sure that's the first thing that everybody encounters. And then, the sine taper is something that is somewhat popular, that is optimal in this very specific sense. And then what I'm showing you in black is this thing called the Kaiser window, which is the nearly optimal thing in the sense of concentrating as much mass of the normalized function in some ball around the origin as possible. And you can see in the spectral windows here, right? This is on the log scale. So we're looking at 15 orders of magnitude of concentration in this kind of small region around the origin. And so convolving that little tiny thing that almost looks like a delta mass with your spectral density will produce a strong, and maybe I'll even go back here, strong but very distinct form of bias, right? And so you can see that I'm convolving this thing that is, in some sense, a true delta mass with something that is not quite a delta mass, and so I get this little kind of rectangle area instead of a true mass. But I think, especially when even visually you know what that bias should look like, there are worse things. So, what makes a G a good choice here? Well, like what makes a G more concentrated in the Fourier domain? Kind of a classic Fourier analysis question, right? It should be kind of a smooth periodic extension. It should certainly be smooth on the domain 0, 1. The usual stuff. And I'm happy to talk more offline about the hardcore Fourier analysis questions. But I think that something that I imagine anybody who works in time series has tried before is they say, okay, so I'll pick a G that makes a good spectral window for a time series estimator, right? Like I'll pick a Kaiser function, which is you can evaluate in closed form. And if I have irregular data, then I'll just say that I'll pick weights that are just the G function evaluated at my time points. And will this estimator inherit nice properties of G the way it does for a grid? And the answer is no. I have to imagine that many people have tried something like this with irregular data before, and they've looked at this estimator that completely kind of like hits this noise floor only a few orders of magnitude away from where the spectral density peaks, and you look and you say, that's a completely unusable estimator, which it is, and then you say, okay, I guess Fourier methods don't work for irregular data. And that's certainly how I felt for the first however many years of my career. I remember right out of my undergrad in like 2016, I was working on a project with irregular data, and I reached a figure like this, and I was kind of like, okay, and the PI at the time was kind of like, okay, yeah, you proved it doesn't work, move on, and that was it, But I think that the issue with that dismissal is that there's kind of like a high level conceptual mistake. And to examine and kind of peck at this mistake, I think we should step back and say, why does picking a good G, where a good G means something that has good properties in terms of its Fourier transform, right? Like that Kaiser function has a Fourier transform that's very well concentrated around the origin, right? Why does picking a good G sometimes give me a spectral window that inherits those nice properties of the actual Fourier transform of G? And the answer is because sometimes that sum effectively up to scaling is like a trapezoidal integral, right? And so if your G is very smooth and has very nice behavior at the endpoints, the trapezoidal rule is super exponentially convergent. And then this is, this is again something that I think for statisticians in particular, you probably do one lecture in one course on numerical integration or something, right? And so everyone sees trapezoidal and they say, okay, it converges like big O of h squared, where h is my step size. But the truth about the trapezoidal rule is that it converges everywhere between that rate and super exponentially fast. And the proper analysis for trapezoidal rule isn't about local Taylor approximations, which is always going to be very pessimistic error bound. It's about looking at how rapidly the Fourier series of the function you're integrating converges, right? And so for a nice G, this H alpha will be to numerical precision equal to the to the analytical Fourier transform. And so then the question now is, when you have irregular points, can I write that sum and expect to inherit the nice properties of the analytical properties of the Fourier transform of little g? And the answer is no, certainly not. And the explanation about why is kind of something that is again about the brittle structure of trapezoidal integration. And I'm happy to talk offline about that a bit more. But let me cut to the chase and say, here's just like a different way to conceptualize designing these weights. Rather than picking a g, defining my weights to just be this my window function defined at these time points, and like squeezing my eyes shut and being like, let's hope the spectral window has those properties. What if we instead directly design our weights just to achieve what we want in that spectral window, right? And so instead of sometimes defining my weights in terms of little g, now I define them directly in terms of its Fourier transform by saying, I want my spectral window to be approximately equal to that analytical Fourier transform on some domain that I'm going to have to choose carefully. And I'll have more to say about that later. And so do weights alpha that achieve this exist? Sometimes. But like often yes. And again, something that I won't have a lot of time to harp on here, but I'm happy to discuss offline with anybody, is that the dance you have to play is you need to pick a G that is appropriate for the domain that your data lives on. And so maybe that gives you some indication of the dance here. But like, here is an example of where I pick little g in this figure to be a Kaiser window again. And if I write like a regular unweighted sum, right, where I pick my weights to be this thing, the weights look very reasonable in the time domain, right? But when I look at the spectral window, I only get a few orders of magnitude of concentration, and then I kind of get garbage very, very quickly, right? And so any estimator that I have using a weight formulated in that way is convolving this monstrosity with my spectral density. So that's not going to work. That's not going to work well. Why should it work well, right? And so the irregular trapezoidal rule is something that people in the imaging community use a lot. I think they call them density compensation factors. Better than nothing, but again, not really conceptually, I think, the right perspective. Whereas in the estimator that I'm showing you here, I picked omega to be 75 in this figure. And so you can see that when I ask for these weights to satisfy this approximate inequality, and I use a reasonable choice of a window function g, I can achieve that approximate equality to effectively numerical precision, and I can get crushingly good concentration. And so, I think really there's not a huge new insight here, right? I think it's kind of just a shift of perspective where people want, I think, typically to write weights for some kind of weighted Fourier contrast estimator in some way that is intelligible, like component by component, right? And the compromise that I'm suggesting here is to say, give up on interpreting the component by component things in your weights, right? So like when you look at the weights here, you can see I've got some of these huge jumps. Why should the weight for this point be, an order of magnitude or whatever bigger than the weight for this point? And the answer is, don't think about it. I don't know. It's a solution to a linear system. It has something to do with the spacing of the points, some extremely complicated property of some kind of like Cauchy-like matrix that's like 1 over xj minus xk in the entries. And I can talk more offline about that if you want. But suffice to say, there's some enormous abstract matrix that's dictating what those weights should look like. But that's okay. I think, right? So long as I can compute those weights and they behave the way I want, then I can make that compromise. Yeah, please. Uh-huh. Yeah. Uh-huh. Hmm. Yeah, that's interesting. And I also should say all the figures I'll show you are for IID uniform points. And this is actually something that Rob Novak asked me when I was talking to him at Wisconsin at one point. He said, if your points are IID uniform, that's the perfect Monte Carlo estimator. And yeah, and the reason it doesn't work is because just the variance of Monte Carlo estimator is too high, right? Like if I want to make something that is whose absolute value is on the order of 10 to the negative 18 or something like that, right? So I want to sum up a million numbers and I want it to be that crushingly close to zero. It has to have basically no variance, right? But the variance of the Monte Carlo will go down like 1 over root n, right? And so there's just it's always going to be too variable to ever make something that's anywhere near close enough to zero to kind of achieve that kind of good concentration in a, like if you interpret it as a Monte Carlo integral. But that's I mean you're right. And so like the bizarre thing about this whole thing, and I actually will show you a theorem later where I do exactly assume points are random from an arbitrary distribution, but they are IID, is that that randomness ends up getting baked into like the norm of the weight vector in like a reasonably complicated way. So rather than having variance now in the spectral window, I have variance in the norm and a few other kind of derived properties of the weights that will impact properties of the estimator in a way that I'll clarify later. But yeah, but you're right, and I should emphasize uniform points and the it's just too hard to make a Monte Carlo integral ever really that reliably close to zero, right? I mean, and that's kind of what you're seeing exactly here, where when you square it, it's 1e-5. That's not horrific, but it's not close enough to zero. Yeah. Ah, that's interesting. I think I see. Maybe we could talk later, just to make sure I understand your suggestion. But I think that makes sense. Yeah, cool. Okay, I'm going to think about that. So cutting to the chase, if I define my weights in this way, now I'm going to go to continuous time now because if I'm irregular in some sense, I don't really have a Nyquist frequency anymore. So going to continuous time, I now interpret the variance of my Fourier contrast. That's kind of just like this, right? Just this weighted sum here. Exactly the same as I would, where I'm just convolving H alpha with the spectral density on the entire real line, and so everything looks good, right? I designed it to look. I designed the weights so that I could think about that expectation as convolving some very near delta mass function with my spectral density, and that is what I get, right? And so I mean, and so in this particular case, right, I've got about 15 orders of magnitude to play with, in the sense, but before the broadband bias kind of takes over. And so here's 9 orders of magnitude that I'm asking for, and that all works out. So conceptually, no surprises. So the thing that regrettably is kind of unavoidable, and that I think is kind of where a lot of the fun error analysis comes in for this estimator, is that someone might say, like you're thinking, so there is no Nyquist. Can I just estimate the frequency at crazy high, crazy large z? I mean, can I estimate the spectrum at crazy large frequencies z? And the answer is, I mean, you can compute it, but you're not going to get something useful back. Like many things, the computer will give you a number, but that's, all you've done is made the heat death of the universe like that 1 picosecond sooner sometimes, right? And so because of some kind of like hard information theoretic limits that again, I'm happy to discuss offline, I can only resolve a frequency interval that's about ON in length when I have n points, right? And so, Shannon-Nyquist, whatever. And so what's going to happen is that I'm going to have some frequency band that looks like this, where I do not have that approximate identity, right? Where H alpha is completely uncontrolled and not equal to G. And in the kind of the one sentence explanation, right? Like if you want to interpolate something that oscillates n times, you need at least like an n-degree polynomial, right? And if you think about this from a Gaussian quadrature perspective, if I have n points and I want to, like resolve the zero frequency and a frequency that is omega equals n squared or something like that, I can't do both those things at once because I can't resolve that high oscillator of a frequency n squared, right? Like I'm gonna have n squared wiggles, but only n points to choose from, and so I can't resolve it. So I can't do that integral accurately. And so with this in mind, it's natural to ask, what does this H alpha function look like when I'm not controlling it? Because this is going to be, I call this the super Nyquist aliasing bias. This is all going to be noise that comes in and pollutes my estimator. It's like some positive random variable that comes in and bonks the thing that I'm trying to resolve, right? And so what does H alpha look like? What frequencies are easier or harder to estimate? And what process features are going to impact the size and kind of problems that the super Nyquist aliasing bias introduces? Yeah, please. Mm-hmm. Well, sort of, but let me go to the next slide. Here, and so it's exactly to your point. Outside of my controlled frequency band, I don't. It's exactly like you say. I don't have anything that is structured. I get and you can imagine when all those things are IID, right? You have nice CLT type characterizations that make this quantity H alpha very, very flat and concentrated around the norm of your weights outside of these controlled frequency bands. And so it's not exactly an identifiability issue, I would say, or at least that's not how I would think to characterize it. But I would say that the problem is that integrating the spectral density against like this thing that's kind of flat spaghetti hovering around that weight norm is going to bring in something whose variance may be much larger compared to the variance of the Fourier contrast I'm trying to estimate, right? Like like the spectral density maybe is 1e negative 8 or something like that, right? And so I want to create some linear contrast whose variance is 1e negative 8. But if the size of the super Nyquist aliasing bias is likely on the order of 1e negative 6, then I'm not going to be able to really see the variance of the thing I'm really trying to resolve is going to be so much smaller than the variance of my kind of nuisance bias that I'm going to be unlikely to kind of pick out that signal. And so just, like we were saying earlier, I'm going to assume that my points are under some distribution. And I'm hiding a handful of like technical assumptions here. Like the technical assumption on P is that the characteristic function decays rapidly enough that phi of omega minus phi of omega squared is I'm going to approximate that with just phi of omega. So like I decay rapidly enough in that sense. And then a few other things about like support or whatever, right? But under some reasonably mild technical assumptions, I kind of have this relative size, like Chernoff type bound saying that, and I think the way to interpret this is to say, let's say you pick beta is equal to 1. Like I'm now saying, what's the probability that my super Nyquist aliasing bias is at least as large as the thing that I'm trying to isolate in terms of like I want a linear statistic whose variance is like S. And so in that sense, you kind of think about it as like, what are the odds that I drown out the signal that I'm trying to see with variance coming from regions of the spectral of the domain that I'm not controlling. And that tail bound kind of looks, it has this is not a sharp bound. I think there's probably I'm sure there's a prefactor that I've missed in here, probably on the like something like a factor of 2 or pi or whatever, right? But I just think I kept the theorem as it is here because it has all the most important bits, right? Some ratio of the spectral density where I'm asking, and then an integral of the spectral density over the uncontrolled region, and then the norm of the weights comes in here. So if they're very large, then I lose a lot of power to conclude that I'm very likely to get something where the super Nyquist bias is not drowning out the signal I'm trying to see. And I think the sketch is very illustrative, right? So you imagine if I take this z and I just drag it further and further and further this way, right? I'm going to be integrating this spaghetti part of H alpha against the part of the spectrum that has the most mass, right? So the further out I go, the less well I am isolating the uncontrolled parts to hopefully regions of the spectral domain in which the spectrum is small. And so I'm asking for a statistic, I'm asking for my linear statistic to have a variance that's smaller and smaller the further out I go. And the super Nyquist aliasing bias is getting larger and larger as this spaghetti part creeps further and further and further closer to the origin. And so that's kind of the dance here. And so the simple corollary, right, is I can effectively write my expectation in terms of the survival function and just tweak that Chernoff bound to write something that is sort of the flavor of a Matern spectral density, right? So if I'm Matern-like in the tails, yada, 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 I get some control on the expected value of this aliasing bias that kind of drowns out my signal. And as you might expect, like if your nu is very small, like near 1/2, and so your spectrum decays very slowly, you might need to have 10x as much data to make that expectation go down by an order of magnitude or something like that. Whereas if nu decays quickly, you might be able to double your data and gain an extra digit effectively in terms of mitigating the size of that bias, which I think is intuitively reasonable, right? If there's more and more high frequency energy in your process, right? Like the marginal variance of that data is spread out in the spectral domain in a wider region, then you need more data to resolve enough frequencies that you can kind of start to control those relevant frequency bands, right? And so that's kind of the story, the upshot here. And here's just like I think kind of a nice figure. So this expectation, as you can see from the squiggly lines, is actually a Monte Carlo estimate of that expectation. But I think you can really see that the variance of my S hat is the super Nyquist plus the spectral density. And spectrum goes down, super Nyquist aliasing goes up. And so I kind of just hug those two things, and I'm sort of just almost getting the maximum of those two at the extremes of low and high frequencies. So okay, I've really tried to reduce the computation part of this talk because it's brutal. And so I'm gonna take like a hard left turn into some computation. Before I do that, though, does anybody have any questions? Oh yeah. And if you want to talk offline, we can nerd out. Because this is a very restrained slide from me as far as the computation goes. So in some sense, thank you very much. I can write a linear system to determine my weights alpha, right? It's not going to be square for some conditioning and technical reasons, right? But I can oversample in the frequency domain, and I can write a linear system, and that will be reasonably close, at least to numerical precision of what I'm looking for, right? And so I can use a non-uniform FFT to get a matrix vector product with f in n log n time. I can use a Krylov method to solve that least squares problem only using matrix vector products with f. And so that's that now, like the entire pipeline means I only need matrix vector products, which I can do fast, and I can get my weights. And then with a little bit of a clever transformation of the linear system, I can write it in such a way that I can build a good preconditioner. And happy to talk about that offline. The preconditioner stuff is really where the pain is. But the issue that I think many of you might look at that and say is that there's a lot of really brutal and accurate, like sharp theory about the condition number of the non-uniform Fourier matrix being exponentially poor with a maximum gap between points, right? So you should think about F as being rank n over 2, say, which is kind of the worst case, right? The null space is too big to resolve using some fast tool, and the column space is too big to resolve using some fast tool. So the real dance here is that I need to pick my big G such that B, like this vector that is that nice Fourier transform, lives in the non-degenerate column space of F. And then with a good preconditioner, because again, the eigenvalues of the F Hermitian F are obnoxiously either very concentrated near 1 up to normalization or basically 0. And so it's a hard linear system. But if I make sure I'm in that non-degenerate column space and I make a good preconditioner, I can converge in a handful of iterations. And so here are some runtimes, for example, where I pick my points to be IID uniform. And on the left, so it takes me like 45 seconds for 250,000 points to compute the weights to machine precision. That's slow compared to 1 FFT, but it's survivable, right? And then if you have a gappy grid, for some technical reasons that, again, I'm happy to talk about offline, you don't need a preconditioner. And your system is very well behaved. And so that's just FFTs, just NUFFTs. And so for, in 1 second, I can get the weights for 250,000 points. So that's not so bad. So the whole pipeline then for computing this estimator, and so for the sake of time, I want to get to dessert. So just to say, you pick your function G that has nice Fourier properties. You pick some frequency, that's the largest one you can resolve based on Shannon-Nyquist-like principles. Happy to elaborate on all of these details offline, by the way. You discretize your sum and your integral, right? You make your linear system. You solve it using your NUFFTs and your Krylov tools and all that fun stuff. And then one weighted NUFFT, square those things, and you've got your estimators. So here's our quick shootout. So I'm on a lattice, and I'm just going to add jitter, and we'll look at like the weighted sum and the estimator I'm introducing here. This is something that astronomers like. And so I got to put this here because I'm trying to pitch it to some astronomers. But maybe for the sake of time, I'll skip that discussion here. So no jitter. Everything works as expected, right? Add a little jitter. You can see I'm starting to lose some accuracy in that normal weighted estimator. Add more jitter, and suddenly the thing that might be the most scientifically useful, picking out this little spectral line here, is completely drowned out by that super Nyquist aliasing bias, right? So as that jitter goes up, like I just slowly lose the ability to resolve finer features at higher frequencies, right? And so the estimator that I'm introducing to you here does not have those issues. So let's see here. Okay, higher dimensions, that works. And so this was 1 million points that I computed in 4 minutes, but the preconditioner in 2 dimensions takes more RAM. So it's like 20 gigs of RAM. I really like things to run on laptops, but this had, some people have laptops with that much RAM, I suppose. I don't, and especially with the market now, I don't think I ever will. So unfortunately, you might need some bigger metal for that. But anyway, I really want to get to this dessert here. Okay, yes, 2D, it's fast. Okay, so here's the pipeline, like done correctly. I have this beautiful vertical wind profile data. Thank you very much. It's this incredible sensor. It's a Doppler LiDAR sensor, right? Like it looks up and it shoots all these photons up. They bounce off of aerosols. They come back, and from the measured blue or redshift, I get the vertical components of the wind velocity, like in that direction that sensor's looking, right? And so I get this really high resolution space-time data that is describing these vertical wind profiles. And what's annoying, right, is that these instruments that are not powerful and they're not complicated because they need to be affordable, there's all sorts of like funny little jitter. They've got weird gaps. Every hour when they start writing to a new file, the timestamps can get kind of misaligned. And so you can do something very annoying and do some manual bookkeeping and make a Welch estimator if you're familiar with that, and do those simple things. Or you could just hand it to my code, raw timestamps and raw measurements, and look at a nice estimator for the spectrum. And what's really cool is that when you look at this, I think you look and you say, okay, I don't think a Matern model is right here. That looks really sharp near the origin, right? And so for those of you in Suhasini's time series course, or maybe some others on, I kind of don't, I don't know the full catalog is. Ah, oh yeah, okay, all right. Well, many courses then, right? Like you have an integrable singularity at the origin in your spectral density. You might call that a long memory process, right? So I look at that and I say, I think that might be a singularity. Let's see if the modeling bears out here. So I'll write this thing that I'll call a singular Matern model, where I put an integrable singularity near the origin. And again, I just have to, 10-second flex about the numerical integration package. This, like doing the Fourier integrals is the only way to numerically reliably evaluate that covariance function. This is like this kernel extended precision line here that you can see completely breaks. I mean, certainly a covariance function that's 1 at 0 and 1,000 at 0.8, that's not a valid covariance function, right? This is, like you can write this Fourier transform in terms of generalized confluence hypergeometric functions, but don't. It's not going to work. You cannot run poor conditioning. You can't. So instead, you sum up trillions of numbers really fast with non-uniform FFTs. And so that's what we do here. And I fit a normal Matern and the singular Matern model to this data. And what's interesting is that the estimator picks a pretty big singularity, right? That's very strong long-range dependence, right? And what's interesting, though, is that the parameters in general compensate, and so the spectral densities don't look very different. But what is very different is the covariance function. And I think that meteorologically, there are plenty of reasons to believe that that marginal slice could exhibit long memory behavior, right? Like, again, and I think a fun exercise to give someone is you say, write something that is Markov in space-time, but marginally in just time has long memory or something, right? Like, and you'd think that that's not really possible, but it's not too hard to cook up. And so I fit this model. The likelihood is materially better. It's only a few thousand data points, right? So I think 50 likelihood units, I'll take that. And physically speaking, this model with the singularity is mean square differentiable, which I think is, again, maybe more parsimonious with what a meteorologist would expect, whereas the normal Matern model is not. And you can really see the normal Matern model kind of saturates in a way that the data really doesn't seem to indicate. And so this is all just to say, this is the pipeline that I want. And I'm trying to take bites out of, right? Like, I want to do an exploratory analysis. I want to figure out what, thank you very much, is an appropriate model to fit. And then I want to specify and fit it, not the other way around, And so I have 1 minute, so let me wrap up. I'm kind of introduced this exploratory estimator that is robust to irregularity, kind of by design. And in terms of the practical costs, the maximum Nyquist-like frequency gets reduced by a factor of 2, but otherwise there are no real downsides in comparison. And I'm happy to talk about that factor of 2 offline with those of you who are curious where it comes from. I can compute the estimators pretty fast, but there are a lot of challenges, right? And if in a weird domain, picking a good G is hard or impossible. Combining, if I have 1 trillion points in one tiny neighborhood and then 5,000 points in a huge neighborhood, there's not one set of weights that will, those two problems are just different, right? Trillion dense points resolves very high frequency, very poor resolution. Spread out points is kind of the opposite, right? So I think writing, heterogeneous estimators that try to take advantage of what the data can tell you in different areas of density or sparsity, interesting. Can you make this for time free? Lots of ideas here. But it feels like a good first step. And so please take a look at the paper on arXiv or chat with me. Here are my references, and thank you very much for your attention.
Thank you for the great talk. Any questions? I have one question. Can you please remind us of your spatial dimension and temporal dimension of your research?
When you say dimension, like how large data sizes are, or like am I working in 2 dimensions in space and 1 dimension time, or?
Typical of the spatial temporal data, right? It's like a
Ah,
multivariate time series data.
sure.
Multivariate dimension, we call it the spatial dimension. So what's the spatial
I
dimension?
see. Yeah. So in this LiDAR data, I have one space dimension because it's just straight vertical in time, and I get maybe like 40, 50 measurements before the noise of the sensor is makes the data unusable. Um, and then in time, I've got measurements like every 1 second or something like that. And so I got like 5 million points per day maybe.
Temporal dimension, how many time series points?
Oh, yeah. So the so each day of the sensor produces about 5 million points, I guess total. And so then, I'm gonna do this math wrong in my head. If it's about once every second for 24 hours, yeah, a bit, yeah. So certainly large. But non-uniform FFTs are a very mature tech, and so computing weights at that size is not a concern.
Dimension and
Mm.
it's also it's large the spatial dimension. I
Mm.
wonder if your proposed spatial method is scalable in these two dimensions.
Oh yeah. So here's an example where I do 1 million points on an IID like IID uniform points, which I regridded here just to show you an example sample path, and I computed the estimator here in 4 minutes with 1 million points and 20 gigs of RAM, I should say. So yes, yeah. Oh, thank you.
Tell me, thank the speaker again.
Thank you very much. Thank you. So should I kill the Zoom here or something or?